So if we have these three vectors, 1, 0, 1, 0, 1, negative 2, and 2, 1, 0, all members of what we would call R3, because each one is a 3 by 1 column of real numbers. With those vectors, have you seen the term span yet? Has that shown up in class at all? Not yet? The idea of the span of a collection of vectors, in this case, we say the span of V1, V2, V3. What this means is the collection of all vectors that can be built or created as, have you seen the term linear combination yet? So if we're talking about a linear combination of V1, V2, V3, what do we mean by a linear combination? What could you do with those that we would call linear? What are some operations you can do to vectors?
Adding, multiplying them, subtracting them.
Yeah, you can multiply, specifically multiply each one by a scalar. So let's say C1 times V1, another scalar C2 times V2, and a scalar C3 times V3. And they can be added or subtracted. Although we can write it as just adding, because we can cover subtraction by just having those C values be negatives. Cross product, yeah, we could take a look at that also. So this would be called a linear combination. Linear combination of these three vectors. And you can do this for as many vectors as you want, of course. A linear combination of just one vector is also possible. A linear combination of one vector just means scalar multiples of that one vector. Scalar multiples or linear combination of two vectors would look like this. Linear combination of three vectors would look like this. And you can extend that to as many vectors as you want. But the idea is a linear combination is a way to build new vectors using the few vectors you've already got. The span of a few vectors means a collection of all vectors that can be created as linear combinations of those few vectors. And how many vectors would that be? If you start with three vectors, how many possible ways are there to make a linear combination of them? If you could theoretically list out all possible linear combinations, how many linear combinations would there be? Well, what sort of things are these C1, C2, C3 supposed to be? 6? Could we list out all 6 of them? Are there only 6 possible sets of coefficients you could use here? How many possible values could there be for C1, for C2, and for C3? Yeah, infinitely many possibilities. Because C1 could be any real number, C2 could be any real number, C3 could be any real number. In fact, we could even extend this to allow complex coefficients as well, but for now we're just going to look at real values. But either way, we have infinitely many possible linear combinations. So the span of these three vectors is a set of infinitely many vectors. In fact, you could even think of span as being sort of a function or an operation. Span takes a few vectors as input and creates an entire space, an entire universe of infinitely many vectors as output. But specifically all the vectors that can be formed as linear combinations of just those few vectors. I usually think of these vectors as being like building blocks. Like if you imagine these as like 3 types of Lego bricks. The span of those 3 types of bricks is the set of all possible things you can build, all possible sculptures or whatever you can build using just those 3 types of bricks. And of course, you can have as many of each one of those types of bricks as you want, but you can only use those 3 types. That's what we mean by the span of a collection of vectors, the set of everything you can build, all the vectors you can create using just linear combinations of those few vectors. Any questions on that so far? And ideally, we'd like to be able to categorize those infinities, because just saying there's infinitely many vectors doesn't really give us much useful information. We want some more specific information about that infinity of vectors. Specifically, we typically want to know what sort of region we're forming. When we're looking at all possible linear combinations, we want to know, do we just form a single straight line, or do we form a plane, or do we form a 3-dimensional space, or something even more? In this case, it can't be more than 3-dimensional because we're talking about a 3-dimensional universe here. But within that 3-dimensional universe, maybe these form just a single straight line, maybe they form all of some plane, or maybe they form all of R3, the entire 3-dimensional universe. Those are really the only options here. If they had been members of R4, if these had been 4x1 vectors, we might have more possibilities, or maybe even larger. But in this case, let's take a look at what this looks like on a graph. Because in 2 or 3 dimensions, you can actually graph it. And it's often useful to get a visual look at what's actually going on here. So if we try graphing these with just a conventional x-axis, y-axis, and z-axis. I'm going to make some notches here. Not sure this is going to be very well to scale, but it's just a sketch anyway. So if we mark these, we've got V is 1, 0, 1. So 1 in the x direction, 1 in the y direction. Oh no, that's not right. 1 in the x direction, 1 in the z direction. Let me draw that. So 1 in the x direction and 1 in the z direction. So there's the V1 vector. V1 is going forward and up. And then V2, 0, 1, 2. That's 0 in the x direction, 1 space in the y direction, and 2 spaces in the z direction. So V2 is flat on the board going diagonally like this. V1 is coming out of the board and upwards. And then V3, 2, 1, 0. By the way, if we stop here, if we just have, in fact, let's take a look at just V1. If we have just V1, what would linear combinations of just V1 look like? If we're talking about the span of V1 alone. What would the span of just one single vector look like? What would that mean?
That is multiplied by a scalar.
Sorry, what was that?
That is multiplied by a scalar?
Yeah, it's just that vector multiplied by a scalar. So some scalar times that vector. And of course, that scalar could be anything. So we might write that as this format. Does this format look familiar? Have you seen this sort of structure before? This is often described as set builder notation. It's a convenient way of describing a set of infinitely many things in a very compact space. The vertical bar here would be read as such that. And typically the way this works is you've got curly brackets to represent this is a set, a collection of things. The left side is describing what sorts of things are members of the set. The right side is describing any conditions that have to be true in order to really count as a member of the set. So this is the set of all things that look like V1 times some scalar, such that, and then this says that scalar could be any real number. So basically we're just looking at all real valued multiples of V1. And if we were to graph that out, if we draw vector V1 and then maybe 2v1 and 3v1, or maybe 2.5v1, or maybe even some negatives. Maybe we could draw negative v1, negative 1.2v1, negative 4v1. If we just draw out all these scalar multiples of v1, which, and there are of course infinitely many of them, what shape are they forming though? Yeah, these infinitely many scalar multiples of v1 are forming a line, because all scalar multiples of v1 are going to be in the same direction as v1, straight out and up, or the exact opposite direction if we're taking a look at a negative multiple. But all these multiples of v1 are forming a straight line through the origin. So the span of v1 is a straight line. That is all the vectors that are along that straight line. Specifically, a straight line through the origin. But let's add in vector v2 as well. So if we're taking a look at the span of v1 and v2, in this case, we're now looking at a collection of vectors that are linear combinations of both of these. So that's going to look like something times v1 plus something times v2. That's the sort of thing we're looking at. We're looking at things that are something times v1 plus something times v2. And c1 and c2 are basically just placeholders for now. Then we're going to say such that, and then describe what sort of things c1 and c2 have to be. Specifically, the only restriction we're going to put on them is that they are real numbers. Later on, we might look at some more detailed restrictions, like we might say such that, and then maybe c1 and c2 have to be related to each other in some way. Maybe c1 has to be 2 times c2, or maybe c1 and c2 have to be same absolute value but opposite directions. But in this case, we're just saying c1 and c2 have to be any real numbers, no further restrictions. In that case, if you can add something times v1 plus something times v2, anything times v1 plus anything times v2, and look at the results, what sort of shape would you get from those two vectors? What sort of region could you get to? If you can walk as far as you want in this direction and as far as you want in this direction, it's not just going to be a line anymore, right? Because v1 forms a line, but then you can leave that line in the v2 direction. So what collection of points could you get to there? What sort of shape would that be? If you can go as far as you want in the v1 direction, and then from there as far as you want in the v2 direction. Or the exact opposite direction would also work. Yeah, we get a plane. And I wouldn't even restrict it to triangular, because it's not like we're getting only this triangle. You can also go like in the v2 direction, and then from there in the negative v1 direction. Or you can go in the positive v direction and then go in the negative v2 direction. So you can go as far as you want in this direction or backwards, and as far as you want in this direction or backwards. So you're getting an entire infinite plane, which would be a plane containing those two vectors. And in general, if you've got two vectors in different directions, they are going to form a plane. Like let's say you've got this direction and this direction. Those two vectors form a plane that includes both of those two vectors. If you choose two other vectors, you can still form a plane that contains those two vectors. Any two vectors you want, you can create a plane. The only exception is if the vectors are parallel to each other, because then there's infinitely many planes that would work. So two non-parallel vectors define a unique plane. If they're parallel, they don't really define one specific plane. There's infinitely many planes that would work. But in this case, we have two non-parallel vectors, and so they create a plane. Any questions on that so far? Yeah, go ahead.
So would there be any like scenario where you would have two lines that don't form a plane and that are just like intersecting points or something?
Well, in this case, it would be if you had two vectors that were parallel to each other, like in the same direction. Like, let's say instead of looking at 101 and 01 negative 2, let's say we looked at 101 and another copy of 101. Or if we had 101 and 202. 202 is the same direction, it's just twice as long. So it doesn't really add any new information. I tend to think of the direction of a vector as being like information it provides. Like V1 provides information in this direction. V2 is a genuinely different direction, so it provides new information that V1 didn't already have. By adding in new information, we're allowed to leave that line and go somewhere else, specifically forming this entire plane. In fact, that idea of information, I think it's probably best to think of it as information about how to get somewhere. Knowing vector V1 allows you to travel in this direction. Knowing vector V2 allows you to travel in this direction. If you can travel in both of those directions as far or as little as you want, you can get to anywhere on that entire plane by going some amount in the V1 direction, then stop, and from there go some amount in the V2 direction. So the plane we're talking about is the set of all locations you can reach if all you know how to do is travel in these directions, or the exact opposite direction because negative scalars also work here. So that's why we get a plane here. Also, intuitively, how many dimensions would you say a plane is? And how many dimensions would you say a line is? Yeah, line is one-dimensional and a plane, two-dimensional. And the reason why we say that has to do with this idea of span. We were able to create a line by taking the span of one vector. So we say that is one-dimensional. This plane, a plane through the origin. And note that these all include the origin, because you can always get the origin by just using 0 for C1 and 0 for C2. This plane is two-dimensional, and we call it two-dimensional because it requires two vectors to build it. The dimension of some space, some region of vectors, is defined as the number of vectors that are required in order to span that space. So we can build a plane by using the span of two vectors, so we call a plane two-dimensional. You can build a line using just one vector, so we call the line one-dimensional. If we're looking at just a single point, how many dimensions would you call that? Like just the origin. One-dimensional would be a line. If we condense that to just a single point, how many dimensions would that be? Yeah, a single point is technically zero-dimensional because it doesn't have width, it doesn't have length, it doesn't have height. It's zero-dimensional. And in terms of the definition here, it's because you would span, you can't really span just a single point. If you take the span of any number of vectors, you get at least a line. In order to get just a point, you have to take the span of nothing at all. So the origin, the zero vector alone, just a single point, counts as zero-dimensional because it's not spanned by any vectors. It doesn't really contain any information. Again, going back to the idea of information about how to get somewhere, the idea is if you're going somewhere, you start at the origin. So to stay at the origin, you don't need any information. To get somewhere along a straight line, you need one piece of information, how to travel in that direction. To get to anywhere on a plane, you need two pieces of information, being able to travel in this direction and also being able to travel in this direction. What if you wanted to get to anywhere in the entire universe, the entire R3 space? How many vectors would you need there? Like if you've got just these two vectors, you can get to anywhere on this plane. Let me see if I can draw that out. So we've got this plane that keeps going forever in these two-dimensional directions. We've got this plane defined by vectors v1 and v2. But yeah, if we had a third vector, it's because v1 and v2 alone just allow us to travel anywhere on this plane. A third vector would allow us to leave that plane. So adding in this third vector, if we take a look at the span of all three of them, should give us everywhere in the universe, a three-dimensional space. Except there's one slight problem. If we actually take a look at the direction of v3, 2, 1, 0. So that's two spaces in the x direction, one space in the y direction. So there's v3. We can actually build v3 using v1 and v2. Specifically, can you see a way to build v3, 2, 1, 0, using something times v1 plus something times v2? Is there any way you can add something times v1 plus something times v2 to get v3? Yeah, if we take 2 times v1, that gets us 2 times 1 is 2. But what else do we need to add to that? Plus 1 times v2. We get 2 times 1 plus 1 times 0, that's 2. 2 times 0 plus 1 times 1 is 1. 2 times 1 plus 1 times negative 2 is 0. So it's possible to build vector v3 using just v1 and v2 in linear combination with each other. That means that v3 is part of the plane we already have, because the plane is everything you can build using just v1 and v2. We've just built v3 using v1 and v2, so that means v3 is part of the plane we've already constructed. That means v3 doesn't add any new information. v3, again, thinking of this in terms of knowing how to get somewhere, v3 allows you to travel in a direction, but it's a direction we can already get to because it's part of the plane we already know how to reach. So v3 does not provide any new information. What that means is the span of v1, v2, and v3, the collection of all linear combinations of v1, v2, and v3, is still just a plane. v3 does not add any new information. v3 doesn't tell us how to leave the plane because v3 is in the plane we already have. So we would say that the span of v1, v2, and v3 is equal to the span of just v1 and v2, because v3 does not add any new information. So we wouldn't say this is three-dimensional, even though we spanned it with 3 vectors, because the third vector didn't really change anything. The third vector did not provide any new information. If we left out the third vector, nothing changes. So the third vector is kind of redundant in this case. It doesn't provide anything new that we didn't already know from v1 and v2. And this gets into the idea of linear dependency. The fact that v3 doesn't provide any new information means we'd say this set of vectors, v1, v2, and v3, is linearly dependent. The set of vectors v1, v2, v3 is called linearly dependent. And conceptually, I mean, formally, we're going to get into a formal definition of this as well. But conceptually, I think of linearly dependent as meaning these vectors don't all provide unique information. At least one of those vectors is just duplicating the information we already have. Like in this case, we could say v1 forms a straight line. v2 adds new information, causing it to become an entire plane. But if you add in v3, that doesn't add any new information. It's just duplicating the information we already have because it's part of the same plane already. V3 does not allow you to leave the region you've already spanned. Any questions on the meaning of that so far? Then let's take a look at the formal definition of this, or build up a formal definition. What exactly it means to be linearly dependent. We were able to find that V3 happens to equal something times V1 plus something times V2. So that's really the problem here. The problem here is that V3 happens to equal something times V1 plus something times V2. That we were able to build one of the vectors by using the other two vectors we already had. And again, going back to the analogy of building blocks, if you think of this as you've got three different types of bricks, but you've discovered that one of those bricks can be built using the two bricks you already have, that means you don't actually need this type of brick. You can throw away your bucket of this type of brick and still build all the same models using just these two, because these two can be used to make this one. So you don't really need these ones. It might make things faster to build, but you don't really need it. So this is really the issue here, that one of the vectors can be written as a linear combination of the other ones. To make this more general, we're going to put everything on one side of the equation, like subtract V3 from both sides. And we get 2 times V1 plus 1 times V2 minus V3, or in other words, plus -1 times V3 equals, and then what's left if we subtract V3 from this side? Yeah, 0. Specifically, we say the 0 vector. Since it's not just the number 0, it's a vector whose components are all 0. So this is really the big deal here. Linearly dependent corresponds to this idea that something V1 plus something V2 plus something V3 equals the 0 vector. That it is possible to get all those vectors to cancel each other out, to add up to 0. So we can define a linear dependence in terms of not just that one of the vectors equals some of the other vectors added together, but specifically we define linear dependence in terms of all the vectors in the set being able to add up to 0 as a linear combination. If 0 is a possible linear combination of these vectors, we say the vectors are linearly dependent. So let's see if we can formalize that. We say that vectors, I'm going to write this in terms of 3 vectors, but it could really be any number of vectors. So to generalize this, of course, it doesn't have to be 2, 1, and -1 as the coefficients. We could be using any coefficients. What we really want to check here is, with whatever 3 or however many vectors you've got, is it possible to build a linear combination that adds up to 0? If it does, if it is possible to make these all add up to 0, that means some of the vectors canceled out one of the other vectors, which means that other vector wasn't really needed. There's only one slight problem with this definition though. No matter what vectors we're using, what C values will always make this add up to 0? Yeah, if C1 is 0 and C2 is 0 and C3 is 0, that's always going to work. And that's not really very helpful, because if there's always a way to get these to add up to 0, that means there aren't any situations where you can't get it to add up to 0. But the big difference is sometimes setting these coefficients all equal to 0 is the only way to get this to happen. So this is how we're going to define it. If you treat this as an equation, what we want to check is not just, is this possible? Because we know this equation is always possible if we cheat and use 0 as all the C values. What we want to ask is, does this equation have any non-zero solutions? So we want to know, does this have any solutions other than C1 equals 0, C2 equals 0, C3 equals 0, which we usually call the trivial solution. Trivial solution means, yeah, technically this is a solution, but it doesn't really tell us anything special about this system, this situation. So C0, all the C values being 0 always works. We want to know, are there any other ways to make these add up to 0? Like in this case, we found that if you take 2 times this vector plus 1 times this vector plus -1 times this vector, those really do add up to the 0 vector. That's a non-trivial solution, non-zero C values, or C values that are not all 0. So that means that these 3 vectors are linearly dependent. In other words, more conceptually, one of them isn't really needed. We can leave out one of these vectors and the other 2 still have all the information we need. That's really the key here. We're trying to, the whole idea of defining linear dependence or independence is we want to eliminate redundancy, or at least we want to be able to identify redundancy so we can get rid of it to be more efficient. And linearly independent would just mean the opposite of this. Linearly independent means the only way to get these to add up to 0 is by cheating and using 0 for all the C values. Any questions on the meaning of that so far? And typically the way you would check that is by writing out this equation and then trying to solve it for the C values. If you get to the fact that only C equals 0 works, all the C values being 0, if the only way for this to work is for all the C values to be 0, then you know the vectors are linearly independent. If there are other solutions, specifically infinitely many solutions for the C values, then you know that the vectors are linearly dependent. So let's try that in this case. If we write out C1 times 101 plus C2 times 0, 1, -2 plus C3 times 2, 1, 0 and set that equal to the 0 vector, we can treat this as a system of equations. We're trying to solve for C1 and C2 and C3, or not even necessarily solve it. We just want to know, do we get only the 0 solution or are there other non-zero solutions? So to try solving that, you could write this out as a system of equations. For instance, read across the top row, 1C1 plus 0C2 plus 2C3 equals 0. Read across the middle row, 0C1 plus 1C2 plus 1C3 equals 0. Read across the bottom row, 1C1 plus -2C2 plus 0C3 equals 0. That's a system of 3 equations, 3 unknowns. So we could try solving that, or at least partway solve it, and then at least up to the point where we can tell if it has one solution or many solutions. And how would we go about solving that? What's one way we could start solving this system of equations? I think somebody mentioned the augmented matrix and Gaussian elimination method earlier. What would this look like as an augmented matrix? What are our coefficients here? For instance, what are the coefficients of just C1? We've got 1C1, and then in the second equation, no C1 at all. And then in the third equation, yeah, 1 again. Then if we take a look at the coefficients on C2, what do we have? First equation, we've got no C2 at all, right? Yeah, 0, 1 C2, and then -2 C2. 0, 1, -2. And then for C3, what coefficients do we have there? Yeah, 2, 1, and 0. And then we can augment that with the 0 vector, 0, 0, 0. So you can interpret this as each row represents one of these equations. 1, 0, 2 means 1C1 plus 0C2 plus 2C3. 0, 1, 1 means no C1 plus 1C2 plus 1C3. So there are a couple of ways you can interpret this. You can interpret each row as an equation in your system of equations. Or if you take a look at the vectors, where have you seen these columns? Where have you seen these columns before? 1, 0, 1, 0, 1, -2, 2, 1, 0. What are those columns? Yeah, these columns are just the original vectors v1, v2, v3 we started with. So we're really just forming a matrix with those vectors as the columns of the matrix. And then the rows could be interpreted as equations in a system of equations. The textbook, Strang makes a really big deal of this. The idea that this matrix can represent, if you look at the rows, it can represent a system of equations. If you look at the columns, it can represent vectors added together in linear combination. So this vector is written in linear combination, and this system of equations both represent the same augmented matrix. They're just two different ways of looking at it. You could look at the equations as rows, which is what Strang calls the row picture of the matrix. Or you could look at the columns as vectors being combined in linear combination, which Strang calls the column picture of the matrix. Exact same information, just written in two different formats. Which means if you can solve one of these problems, you've solved the other one as well, because they're really the same problem, just written two different ways. So let's try row reducing this. What steps could you take to row reduce this matrix? What row operations would work here? First of all, where would we find our first pivot? If you start from the top row, just reading from left to right, what's the pivot in that row? The pivot has to be the first non-zero term though, because a pivot is as you read from left to right, the pivot means the first non-zero thing you encounter. So as you're reading from left to right, what's the first non-zero number you encounter? Yeah, the 1. This is the pivot of the first row. And the idea is to row reduce this, we want to eliminate everything above and below each pivot. Each pivot should be alone in its column by the end. So if we look in the same column, we've got a 0 here, that's good, we can just keep that 0. We've also got a 1 here. What row operation could we use to get rid of that 1 entirely? How could we modify row 3? Multiplying by 0 would turn this into a 0, but the problem is that loses information. If you multiply an entire row by 0, you're getting rid of all the information from that row, and we don't want to do that. You can multiply a row by any scalar other than 0, because that just changes the values but keeps the same proportions, which is what's important. But in general, the row operations you're allowed to do, you're allowed to rearrange the rows. If you just swap rows around, you're still keeping the information. You're allowed to multiply a row by any non-zero scalar, so changing the size but keeping the same direction. And you're also allowed to add a multiple of a row to another row. So if you think of the pivot itself as a tool that we're using to eliminate this one, what multiple of the first row could you add to the third row to cancel out the 1? If we can take the 1 from the third column and add any multiple of the 1 from the first row, sorry, the 1 from the third row combined with some multiple of 1 from the first row, yeah, if we just multiply that by -1, -1 times this one is going to be -1, which will cancel out this one. So what we're going to do is we're going to take row 3 exactly as is and add -1 times the entire first row. And let's see what that turns into. So the first row, we're not changing. Second row, we're also not changing because we already have a 0 where we want it. Third row, though, we're going to take whatever's in the third row and add -1 times something from the first row. So this 1 here, we're going to add -1 times 1. That cancels it out. This -2 here, we're going to add -1 times 0. So no change. We're just adding 0. And then this 0 here, we're going to take this 0 exactly as it is and add -1 times the 2 from row 1. So 0 plus -1 times 2 would be -2. And then lastly, we've got a 0. We're going to add -1 times 0. That's just 0 plus 0, so it's still 0. So this is the result after we've done that one row operation. Any questions on that so far? So now if we investigate the pivots, first row, the pivot is this 1 here, because that's the first non-zero number we encounter. That pivot is alone in its column. It's the only non-zero number in that entire column. So first column, we're good. In the next row, we look for the first non-zero number. That's this 1 in the center. So that's the pivot for the second row. We want to make sure that one is also alone in its column. We've got 0 above, so that's good, but we don't have a 0 below. So we're going to need to do one more operation to cancel out that -2. Specifically, what multiple of row 2 could we add to row 3 to cancel out this -2? Yeah, if we add 2 times, if we take row 3 and add 2 times row 2, this 1 becomes a 2, which will cancel out the -2. So let's see what that turns into. First row, no change. Second row, no change. Third row, we're taking everything from the third row and adding 2 times the corresponding value from the second row. So 0 plus 2 times 0, still 0. -2 plus 2 times 1, that's -2 plus 2, so that cancels out. And then -2 plus 2 times this one, that's also -2 plus 2, so that cancels out. And lastly, 0 plus 2 times 0 is still 0. So this is our final result. And this is truly reduced row echelon form. We can check by taking a look at the pivots. First row, the pivot is this 1 here. Second row, the pivot is this 1 in the center. Third row, we look for a pivot, but we don't get one. The third row in this case has no pivot because the pivot is the first non-zero number you encounter. And we don't find any non-zero numbers. So we've got no pivot. Now, if we take a look at the columns, thinking of these as coefficients of C1, C2, and C3, C1 column has a pivot, the C2 column has a pivot, but the C3 column has no pivot. What does that suggest about C3 in our original system of equations? What does that tell you about the solutions? Have you seen the idea of a free variable yet? A free variable basically just means a variable in the sense of C1, C2, and C3 here, a variable that could have any real number as its value. The fact that the C3 column has no pivot means C3 could be anything. Once you choose a C3 value, C1 and C2 have to have certain specific values. Like for instance, if you rewrite these rows as equations, C1 plus 2C3 equals 0, so C1 equals -2C3. This row, C2 plus C3 equals 0, so C2 is -C3. But the third row is just 0 equals 0. We already know 0 equals 0, so this doesn't provide any new information. So the restrictions are C3 could be anything, but C1 has to be -2 times C3, C2 has to be -C3. So you could choose any value you want for C3, and then just make the negative of that for C2 and make -2 times that for C1. But the important thing is, because we have a free variable, since C3 could be anything, that means there's infinitely many solutions. There's infinitely many coefficients that would make this linear combination add up to the 0 vector. And that tells us that this set of vectors is linearly dependent, because there's infinitely many ways to get these to add up to the 0 vector. On the other hand, if we didn't get a free variable, if this had turned into like 0, 0, 1, 0, then that would mean that there's only the 0 solution. If the only solution is C1 equals 0, C2 equals 0, C3 equals 0, if the only way to get these to add up to the 0 vector is the trivial solution, then that would mean that the vectors are linearly independent, which means that each one contains unique information that is not duplicated by the others. But in this case, since we get a free variable, that means the vectors are linearly dependent. There's infinitely many ways to get them to add up to the 0 vector. Any other questions on that? And sorry, we didn't have time for the cross product thing. Cross products actually are not going to be seen very much in 22A because cross products only work in 3 dimensions. And in 22A, we're going to look at a lot of higher than 3-dimensional situations as well. But in this case, the main idea is that if you have a plane and a normal vector and another plane and a normal vector, if you take the cross product of those 2 normal vectors, what do you get if you take the cross product of 2 vectors? Cross product of 2 vectors, you get a third vector that is guaranteed to be in what sort of direction? Yeah, the new vector is going to be perpendicular to both of those vectors. So if you have a plane and you create a vector perpendicular to that plane, and you have another plane and you create a vector perpendicular to that plane, you can take the cross product of those 2 vectors. I'm running out of hands here. The result will be perpendicular to both of those normal vectors, which means it'll be along the intersection of the 2 planes. So that's all you really need to do in this case. Create a vector that's perpendicular to one of the planes, create a vector that's perpendicular to the other plane, and the cross product of those 2 vectors will be along the intersection of the 2 planes, at least in terms of directionality. And do you know how to create a vector perpendicular to a plane if you have the equation of a plane? Did that show up in 21C at all? Like if you have the plane that's defined by AX plus BY plus CZ equals D, and you want to create a vector that is perpendicular to it. In general, you can build that normal vector, let's say N vector, by just taking these coefficients, A, B, C. The vector whose components are the coefficients of A, B, or coefficients of X, Y, and Z in this standard form is guaranteed to be a vector perpendicular to the plane itself. So that's a very useful shortcut. Anytime you've got the equation of a plane in XYZ space, as long as you can write it in this standardized format, you can just use the coefficients as components in a vector. That vector is guaranteed perpendicular to the plane. So make a normal vector, a perpendicular vector to each of those planes. Their cross product will be perpendicular to both of the normal vectors, and therefore it will be parallel to both planes. So that's one way to go about finding the vector that's along that intersection. Any other questions on that? All right, then that's it for today. Feel free to contact me online if you have any other questions or if you'd like to request any topics for next time, and I will see you then. You're welcome.